Good day guys, welcome back to Wiki Science YouTube channel. In this video, I'll put you guys through capacitor in an electric circuit, as well as knowing the function or uses of capacitor. We'll also talk about the factors that affect the capacitance of the capacitor. In this video, we'll also talk about the arrangement of capacitor in an electric circuit. So therefore guys, I'll beseech you to pay attention to the end of the video because it's going to really be an amazing video that does what it's time. So guys, let's get started. What is a capacitor? A capacitor is an electric device with two end plates of equal length separated by a space or an insulating material. When it is separated by an insulating material, the insulating material is called a dielectric substance or a dielectric material. So in an electric circuit, the symbol here is used to show the capacitor, in which the two end plates are of opposite charge. One can be of positive and the other is of negative. This symbol can be distinguished from having two end plates of unequal length in an electric circuit. When this occurs, whereby one is positive and the other is negative, we say that this symbol represents a cell or a battery in an electric circuit. Why this symbol is used to represent a capacitor. Now let's move to the aspect of knowing the uses of a capacitor. A capacitor is basically used to store up charges or store up electric potential energy. In this case now, we can quantify the degree at which the capacitor is able to store up charges as the capacitance of the capacitor, which is given as C is equal to charge over the potential difference. In this case, we have our Q to be the charge, we have our V to be the potential difference, and we have our C to be the capacitance of the capacitor. When charge is stored up in a capacitor, the energy stored can be quantified by saying that our E is equal to 1 over 2 CV squared, in which you have your C to be the capacitance of the capacitor and you have your V to be the potential difference. We also have it that a capacitor can still be used in an electric circuit through which alternating current is flowing to oppose the current in the circuit. When this occurs, we say that the capacitor has developed a capacitive reactance, which can be quantified saying that our capacitive reactance is equal to 1 over 2 pi Fc. So in this case, we have our F to be the frequency of the source voltage, and we have our C to remain the capacitance of the capacitor. In the reoccurrence of the capacitance of the capacitor, we can therefore note the unit to which you have your capacitance. The capacitance is always in farad. However, in some cases, the capacitance can be given in microfarad or even in picofarad. When capacitance occurs in microfarad, it is taken as 10 raised to the power minus 6 farad, and the capacitance in picofarad is equivalent to 10 raised to the power minus 9 farad. So at this point now, we can take reference question with respect to this. And question states that a capacitor 8 microfarad is charged to a potential difference of 100 volts. The energy stored by the capacitor is option A 1.0 times 10 to the power 4 joules, option B 8.0 times 10 to the power 2 joules. Option C, 1.25 times 10 to the power minus 4 joules. Option D, 4.0 times 10 to the power minus 2 joules. Now, when you're given a question, the first thing you have to do is to bring out the parameters which you have been given. So the capacitance of this capacitor is 8 microfarad, which as well I've explained that microfarad is given as times 10 to the power minus 6 in farad. So therefore we have the 8 microfarad to be expressed as 8 times 10 to the power minus 6 farad. We have been given also that the potential difference, which is V, is said to be 100. Now what we've been asked to calculate here is the energy stored, and the energy stored is given as half CV squared, in which you have it to be 1 over 2 times C. C is said to be 8 times 10 to the power minus 6 times your V. V is said to be 100 all squared. So here we have that our E is equal to 2 here 1, 2 here is 4. So we have it to be 4 times 10 to the power minus 6 times this is going to give us 10 to the power 4, and therefore we can say that our energy stored is equal to 4 times 10 to the power minus 2 joules. So this is the energy stored by this capacitor. Therefore we have the answer to be option D. We're also going to take another reference question so that we can be able to understand this very much well. A 15 microfarad capacitor is connected to a 240 volt 50 Hz AC source. Calculate the resistance of the capacitor. Now in this case now, we're told that another form of use of capacitor is to offer opposition to the flow of current in an alternating current circuit. So in this case now, we can express the capacitive reactance, which is the resistance offered by the capacitor, to be Xc equals 1 over 2 pi Fc, in which you have your F to be the frequency, which has been given to be 50 Hz from the expression. I will also have the C, which is the capacitance of the capacitor, to be 15 microfarad. We've been told that whenever you have capacitance in microfarad, it is taken to be times 10 to the power minus 6 in farad. So as a result of that, you have this expression to be given as 15 times 10 to the power minus 6. So bringing this expression into the equation we have here, we can see that our Xc is equal to 1 over 2 pi times, you have your F to be 50, and we have our C to be 15 times 10 to the power minus 6. We can easily bring this up, and we have it to be Xc equals 10 to the power 6 divided by 100 pi times 15. That is 2 times 50 will give us 100. And as a result of that, when you use this to divide this, we eventually have 212.18 ohms. And that is approximately 212 ohms. So this is how to get the resistance offered by a capacitor, or you call it the capacitive reactance. So the answer is definitely option D. Now let's take the aspect whereby we deal with the arrangement of capacitors in an electric circuit. Capacitors can be arranged in two different ways in an electric circuit. It can be in series or it is in parallel. When it is arranged in series, the capacitors are arranged end to end. The capacitors are arranged end to end, and the equivalent capacitance of the capacitor is equal to the summation of the reciprocal of the individual capacitance of the capacitors. Now let's see. This is what I mean by series arrangement. And we can have it connected to a source here. Now in this arrangement, they can be the first capacitor, we call it C1. We have this one to be the second capacitor, we call it C2. And this one is the third capacitor, we call it C3. In this case, this can be the positive end here, and this will be the negative. This will be the positive, and this is the negative, positive, and this will be the negative. Meaning that the negative is connected to the positive. So in this case now, it forms a series arrangement. In order to get the equivalent capacitance of this capacitor, we say that 1 over C is equal to 1 over C1 plus 1 over C2 plus 1 over C3. Now I want you to have it in mind. You can have as many as possible numbers of capacitors arranged in series, and in this case it can continue to the end whereby you can have the last capacitor. So the last capacitor can be any number and we can put it as Cn. But with respect to this, you just have just 3 capacitors. So we have to be 1 over C1 plus 1 over C2 plus 1 over C3. So we can take away this one. But don't forget, you can have as many as possible numbers of capacitors. And with respect to this, the potential difference at which travels across these capacitors are different. You can have this one to be V1, you can have this one to be V2, and you can have this one to be V3. Now it shows that the potential difference across these capacitors are definitely different. But something is always constant to all of them, and that is the charge. Do not forget, the charge across this is always equal to the charge across this and to be equal to the charge across this. Meaning that they have equal charge flowing across the capacitor. But what is different here is the potential difference. Now let's take this question for instance. We have it that 2 microfarad, 3 microfarad and 4 microfarad capacitors are arranged in series and connected to 240 volt source. Calculate A. The charge across the capacitors. B. Potential difference across each capacitor. Now let's take this for instance now. Now let's solve this. We have that the first one is said to be 2 microfarad. The second one is said to be 3 microfarad. And the third one is said to be 4 microfarad capacitor. They are all arranged in series and connected to 240 volt source. Now here is the 240 volt source. With respect to this now, what we have to determine is the equivalent capacitance of the capacitors. Now what is the equivalent capacitance? We can have it to be 1 over C equals 1 over C1, because here I have 3 capacitors, 3 different capacitors. I'll take it to be 1 over C1 plus 1 over C2 plus 1 over C3. But if I have more than this, it can continue further. Here now we have to be 1 over C is equal to 1 over 2 plus 1 over 3 plus 1 over 4. And here, taking the LCM of everything, we have it to be 12. 2 in 12 is said to be 6. 3 in 12 is said to be 4. And 4 in 12 is said to be 3 over 1 over C. So we remember have 1 over C to be, we have it to be, that is 13 over 12. Meaning that when you take the reciprocal of both sides, it means C is equal to 12 over 13 microfarad. 12 over 13 microfarad. Now here what they've asked us to calculate is the charge across each capacitor. How do you determine the charge across each capacitor? We can therefore have it that in order to get the charge, our C is equal to charge over the potential difference that runs across everything. Now the charge here can be said to be CV. The charge can be said to be CV. And what is our C? Our C is the equivalent capacitance of the capacitor, which is said to be 12 over 13. Don't forget it's in microfarad, so we have to be times 10 raised to the power minus 6 times, what is the voltage? The voltage is said to be 240. So we have it to be 240. So in this case now, we can now have that our Q is said to be 2.22 times 10 raised to the power minus 4 coulomb. So the charge that which travels through each of this capacitor is said to be the same all through. I will have it to be 2.22 times 10 to the power minus 4 coulomb. The charge is said to be the same all through. The charge is said to be the same all through. But the voltage across each of them is totally different. The voltage across each of them is totally different. So we can still therefore use this expression that your C is equal to charge over voltage. So now when we come back to this expression now, we can say that in order to get the potential difference across each capacitor, we still use this expression that says that our C is equal to charge over the potential difference. The capacitance of the capacitor now here is said to be 2. And here you have to be 2. Don't forget it's in microfarad. That is 2 times 10 to the power minus 6 is equal to. Now the charge here is the same for everything, which is said to be 2.22 times 10 to the power minus 4 over the voltage. So this voltage is for the first capacitor. I'll just call it V1. So with respect to this, my V1 is said to be 2.22 times 10 to the power minus 4 over, here we have to be 2 times 10 to the power minus 6. And that is said to be 111 volts is what you have here. So for this first one, you are having 101 volts. Now let's go for the second one. To get the second one, you use the same expression that your C is equal to charge over your voltage. And now your capacitance is set to be 3 times 10 to the power minus 6. Don't forget, it's 3 microfarad equals the charge. And the charge is the same for everything, which is 2.22 times 10 to the power minus 4 over. Here now what you have is the potential difference of the second one, which you can call our V2. So with respect to this now, we can easily say that V2 equals 2.22 times 10 to the power minus 4 divided by 3 times 10 to the power minus 6. So here now you have it to be V2 equals 222 over 3. 222 over 3, and that is definitely said to be 74 volts for the second capacitor. 74 volts for the second capacitor. So now let's move to the next one, which you have to be C equals Q over V. Now for this third one, you have the capacitance of the capacitor to be 4. So you have to be 4 times 10 to the power minus 6 is equal to, what you have here is definitely said to be Q, which is 2.22 times 10 to the power minus 4 divided by, here you have the third voltage. The third voltage will be said to be V3 is equal to, that is definitely said to be what? 2.22 times 10 to the power minus 4 divided by, it will be divided by 4 times 10 to the power minus 6. And with respect to this, we can easily say that here, that our V3 is said to be 222 divided by 4, 55.5 volts. Now when you look at all of this when you add the voltage across each of these capacitors together, you will surely get this 240. You get this 240 approximately. When the capacitors are arranged in parallel, this happens to be a different case. Now we have it that, let this happen to be the arrangement of capacitors in parallel. When they are arranged in parallel, we can have something like this. So we can have something like this, which is connected to a source voltage here. Now in this case, you have the first one, second one, third one. Please, I want you to take note of this. We don't usually have 3 capacitors in a circuit. We are just making it 3 here. It can be 2, it can be 4, it can be 5, it can be more than that, it can be less than that. So we're just making it 3 here. Now here, to get the equivalent capacitance of the capacitor, we simply say that our equivalent capacitance of the capacitor is the addition of the capacitance of capacitors of the individual capacitors that we have in the circuit. So here we have to be C1 plus C2 plus C3. That's for parallel, in the case of parallel. So here now, we also have it that in a parallel connection like this, the voltage across each of them is the same. The voltage across each of them is the same, but the charge across each of them now is different. You can see what is different here. The charge is different here. So Q1 we have Q2, we have Q3. Meaning that in a parallel connection, the capacitance of the capacitors are different, the charge across the capacitor is different, and the voltage is the same. This is contrary to a case of series arrangement, in which the capacitance of the capacitors are different, the voltage across the capacitors are different, but the charge is the same. So here now we can say that our charge here is also said to be the first charge plus the second charge plus the third charge. The summation of all the charges will give us the equivalent charge across this capacitor. Now let's take a question for instance. The question states that calculate the equivalent capacitance, and the second question is to calculate the charge across each capacitor. And here is what we have. Now in this kind of arrangement now, you see that the capacitors are arranged in parallel. So to get the equivalent capacitance now, the equivalent capacitance here will be said to be C equals C1 plus C2 plus C3. And here we have it to be 3 plus 4 plus 5. And that is going to give us 12 microfarad. 12 microfarad, because the unit here is in, they are all in microfarad. So this is the capacitance of the capacitor. Now if you are now being asked to calculate the charge across each of them, to calculate the charge. Now one thing I want you to take note here is that the voltage here is the same as voltage here, is the same as voltage, and it's the same as voltage across the what? Across the voltage that runs in the circuit, which is 240. So it is 240 volts I have here, 240 volts I have here, and it's also 240 volts I have here. So to get the first one, we say our C is equal to charge over the potential difference. And the first capacitance here is said to be 3. So we have it with 3 times 10 to the power minus 6 is equal to charge over the potential difference, which is said to be 240. So here, the first charge here is said to be 3 times 10 to the power minus 6 times 240. So here we have it to be 3 times 240 is going to give us 720. It's going to give us 720. So we have to be 7.2 times 10 raised to the power minus 4 coulomb. Our charge is always in coulomb. Please take note. Now to get the second one, we still use it that our C is equal to charge over the potential difference, in which you have the capacitance of the capacitor is said to be 4 times 10 raised to the power minus 6 equals the charge, that is the second one, over. So here we can take this as the first charge. So we have it to be over the potential difference, which is said to be 240. So here we can say that our charge is said to be 4 times 10 to the power minus 6 times 240. And 4 times 240 is going to give us 960. It's going to give us 960. So we have to be 9.6 times 10 to the power minus 4 coulomb. That's for the second one. Now to get the third one, we can simply say that our C is equal to charge over V. And here we have that C now for the third one is said to be 5 times 10 to the power minus 6 is equal to charge over V. And our V here is said to be 240. V is said to be 240. So we can simply say that our Q is equal to 5 times 10 to the power minus 6 times 240. And here our Q is said to be 1200 times 10 to the power minus 6, and that's going to give us 1.2 times 10 to the power minus 3 coulomb. So these are the charges that are going to flow through each of these capacitors when they are connected in parallel like this. Now we've come to the aspect whereby we can now denote the factors that affect the capacitance of capacitor. What are these factors? With respect to this, I'm going to give you an equation that which it's going to enable you to answer this question very much well whenever you're given. And the equation is that your C equals AE naught over D. This is the expression, AE naught over D. Now to determine these factors, there are 4 factors that affect the capacitance of the capacitor here. The first one is the area. So the area of the plate affects the capacitance of the capacitor in such a way that your C is directly proportional to your area. Meaning that as the area of the plate increases, the capacitance of the capacitor will also increase. The second one we'll talk about here is the distance between the two plates. The distance between the two plates, which is represented with D. Area is represented with A. From this expression, we can get that your C is inversely proportional to your D. Meaning that as the distance between the two plates increases, the capacitance of the capacitor will decrease. The third one here is referred to as the permittivity. So here, to get the permittivity, you also have it that your C is proportional to your permittivity. Now let me tell you something. The permittivity here is always expressed as permittivity of material over the permittivity of free space is equivalent to the relative permittivity or dielectric constant. This ER is called the relative permittivity, or you call it the dielectric constant. Relative permittivity or dielectric constant. Meaning that for a material now, the permittivity of that material is said to be the relative permittivity times your E naught. From this expression, when your relative permittivity is said to be 1, it means that the permittivity of the material is equal to permittivity of free space. But when it is less than 1, it means that the permittivity of the material is lesser than the permittivity of free space. And when the permittivity is greater than 1, the permittivity of the material will be greater than the permittivity of free space. Now let's compare it with this. From this illustration, we also have that our C is directly proportional to your permittivity. Meaning that as the permittivity increases, so does your capacitance also increase, and as the permittivity decrease, so does your capacitance also decrease. We call it the nature of dielectric material. This is with respect to the nature of dielectric material. Then the fourth one, when we deduce from this formula, is just talking about the geometry of the plate. So as the geometry of the plate also increases, so does your capacitance also increase. So we call it the geometry of the plate. Now we have come to the end of this video. And I believe that this video has been really so much helpful with respect to capacitor in an electric circuit. Thank you for watching. We'll see you next time.